My name is Zhang YunHao. I work at the ByteDance programming language team, and I work primarily on Go runtime and standard library performance issues. And today, let's talk about how to build a high-performance concurrent map in Go. So, since this talk is 25 minutes, so I will only cover the key ideas, and I will not spend too much time on the details. So if you feel confused or you are not sure what's going on, feel free to find me later and ask me about it. So the first question is why we need a concurrent safe map. In Go, we can easily use multiple CPU cores via coroutines, which is good. But when we use multiple coroutines to read and write the built-in map at the same time, unfortunately, the program will panic and show a message like concurrent map read and map write. This is because the built-in map is not concurrent safe. So coming back to my earlier question, we need a concurrent safe map because the built-in map is not concurrent safe and we have concurrent works. So the next question is how to build a concurrent safe map in Go. Well, we have two main implementations of concurrent maps in Go. The first one is sync.Map. It is a concurrent safe map provided by the standard library. It provides most of the usual map operations. The second one is a built-in map guarded by a read-write mutex. We know that for most data structures, if we want to make them concurrent safe, we just need to write them with a mutex, right? And because today we are focused on performance issues, let's do a benchmark and see what happens. Here is the benchmark result for these two maps: the read-write mutex map versus the sync.Map. In each benchmark case, 16 coroutines execute the same number of operations concurrently, but they differ in the types of operations they perform. As we can see in the results, if you want to read and write the map at the same time, the sync.map is not a good choice. Its performance is even worse than a built-in map guarded by a read-write mutex. The sync.map is only faster in load-only case. But why is the sync.map slower in these cases? Well, one common misconception about the sync.map is that it is the best choice for all use cases. But if we read a document in the sync package, we will notice that the sync.map is designed to solve the problem known as cache contention. So it is optimized for the load-only case. In this case, the sync.map is about 3 times faster. But in many real-world cases, we often need to execute various operations on a map concurrently. For example, we might use the map as a concurrent cache. It may call load, range, store, delete at the same time. However, the performance of these two maps is not good enough in this case. So, how can we improve the performance? Since the read-write mutex map has a better performance for now, let's see, maybe we can find some ways to improve it. Let's take a look at the read-write mutex map. We can see the image on the right. Thanks to the read-write mutex, we can now call read operations concurrently. But when multiple coroutines try to read and write the map at the same time, each write operation will block the entire map. And the concurrent programs become sequential. Let's assume each operation takes 100 nanoseconds. And the two read operations can be executed concurrently. So we will use 400 nanoseconds to execute 5 operations. The performance issue is that the write operations will block the entire map. So how can we improve it? Maybe we can find some ways to make the write operation only block a part of the map. For example, a write operation will only block the bucket it is going to, rather than blocking the entire map. So here is a workable solution to this problem. It is called shared map. The idea is that because the bucket is an internal data structure of the built-in map, we can't use it outside of the runtime. And the write operation will block the entire map. So why don't we just create a bunch of maps? Then we can use these maps to create the shared map. In this way, a write operation will only block one submap inside the shared map. At this point, we still have two issues to address. The first one is, how many maps do we need to create to build the shared map? In Go, you can run coroutines equal to the number of your CPU cores concurrently. So we usually create maps equal to the number of your CPU cores. The next one is, how do we ensure different keys will go to different submaps as much as possible? If every item still go to the sync submap, they will still block each other. The key to solving this problem is to use a hash function. When you give a hash function a key, it tells you which submap to go to. So since the hash function is not the main content of this talk, let's just assume we have a real designed hash function that ensures different keys will go to different submaps in most cases. So let's compare the single read-write mutex map to the shared map. We can see that previously we used 400 nanoseconds to execute 5 operations, but now we only need 200 nanoseconds. For the shared map, write operations can be executed concurrently because they are in different submaps. So let's take a look at the benchmark. It is a great optimization. The shared map is faster than the single read-write mutex map in all cases. But what is the price? What is the downside of the shared map? Remember, the shared map is just a bunch of maps. So it will cost more memory compared to a single read-write mutex map. And it also requires a well-designed hash function to ensure different keys will go to different submaps as much as possible. However, in reality, we don't have a perfect hash function, right? Different operations may still go to the sync submap. They will block each other, just like a single read-write mutex map. So how do we solve this problem? Let's review how can we improve the performance of a single read-write mutex map. What we have done is simply divide the potentially locked region from one into multiple regions. A write operation just blocks a part of the shared map instead of the entire map. So if we continue with this approach and try to minimize the locked regions for the write operation, can we further improve the performance? We know that each submap inside the shared map can have multiple items, and the operation on these items will block each other, which means we might have multiple write operations on one submap. So let's imagine a scenario where each submap only contains one item, so it will have at most one write operation for most cases. When a new item is inserted, we will create a new submap, ensuring that write operations do not block each other as much as possible. So how can we implement such a data structure? A data structure like this indeed exists, and it is a classic data structure called a linked list. Since each submap only contains one item, it is more appropriate to call it a node instead of a submap. The right side is the node's data structure. It contains a key, a value, a mutex, and a next pointer. Each node is connected by the next pointer. So what we do next is to implement usual map operations on it, such as insert, delete, and access. We are ensuring that these operations are concurrent safe. To simplify this problem, we assume that this linked list has a head node and all items are sorted in ascending order. This also means that the key tab must be ordered. Now, each node only contains one item, which means each node can have at most one write operation and multiple read operations at the same time for most cases. In this case, we can use atomic function provided by the standard library, making the entire process concurrent safe. That is, for each node, all write operations must acquire the lock before being executed, while all read operations can be executed directly. For insertion, because the only connection between the front and back parts of the linked list is the next pointer. If we control the next pointer, we also control the connection. This means that if we acquire the node lock, then we can insert a new node after it. For deletion, we need to acquire the lock of the node being deleted and its preceding node lock. For read operations, such as load and range, we don't need to acquire locks at all. We can directly use atomic read, which means our read operations are lock-free. There are many details and proofs I can't cover today because they may take around an hour. So if you are curious about what's going on here, you can take a look at my GitHub or just find me later. Okay. So now we have an ordered concurrent safe linked list. And this linked list can execute usual map operations. But before using it, we still need to address a problem. Although accessing the linked list is lock-free, we still need to traverse the linked list to find an item. So its average time complexity for read operation is big O n, which means that if we have lots of items in the linked list, the performance will be poor. So how can we improve the search performance? There's another widely used data structure called skip list. The skip list is similar to the shared map. Well, the shared map is just a bunch of maps. It's just a bunch of read-write mutex maps. The skip list is just a bunch of linked lists. The skip list has multiple layers. Each layer is a linked list. Every time we insert a node, the node will randomly have several layers, and it has at least one layer. The bottom layer contains all the data, and the upper layers are used to improve search performance. This process is similar to binary search, and its average time complexity is big O log n. For example, with the linked list, if we need to find item 12, we need to traverse from 3 to 12, like 3, 6, 7, 9, and then to 12, taking a total of 4 steps. With the skip list, we only need 2 steps, from 3 to 7 and then to 12. So let's combine these two techniques by replacing the linked list inside the skip list with ordered concurrent safe linked list. So it's a new data structure called sync.Map. The sync.Map has the advantages of these two data structures, and it is particularly suitable for high concurrency scenarios. So let's do a benchmark and check out its performance. Here is the benchmark results, the sync.Map versus the sync.Map. We can see that the sync.Map is about 20 times faster than the sync.Map in the typical case, and it is faster in all benchmark cases. Even though sync.Map is much faster in high concurrency read-write cases, given that it's based on the skip list, its average time complexity for read and write operations is also big O log n. Because the sync.Map is based on a hash map, its average time complexity is big O 1. Therefore, the sync.Map may be faster in low concurrency cases. So you need to choose different data structures based on your use case. So let's summarize this talk. The key to improving high concurrency performance is to reduce the locked regions for each concurrent operation. For example, when inserting an item with the single read-write mutex map, the entire map needs to be locked. With the shared map, only one submap inside the shared map needs to be locked. With the skip map, only a few items needs to be locked. So which means if we have thousands of items in the skip map, we can allow hundreds of cores to execute concurrently. So that's it. Thank you for listening, everyone.